Welcome to the U.S. Army Modified Hind Helicopter Photographic Review. Before I begin, I just want to thank the curator of the Southern Museum of Flight for letting me have a private inspection. He, along with the museum staff, went above and beyond to answer my questions and provide unprecedented access to the exhibit. The U.S. Army has long had a requirement to train its personnel in tactics to be used against Soviet military hardware in the event of war. While a few Soviet tanks, APCs, and IFVs were obtained via international sources, Soviet combat helicopters, which were regarded as a serious threat, were harder to obtain. The U.S. Army's training centers originally had to make do with synthetic Hinds, radio-controlled models, Bell JUH-1H's crudely converted into Mi-24D lookalikes, and Orlando Helicopter Airways QS-55s, which were more accurate imitation of the Hind D. The U.S. Army still made every effort to acquire genuine Mi-24s. A Libyan Mi-25 captured in Chad was reported to have been delivered to the U.S. via France for evaluation, but its fate is unknown. The U.S. Army's Operational Test and Evaluation Command, established in November of 1990, or more precisely, the OPTEC Threat Support Activity, OTSA, at Biggs Army Airfield, Fort Bliss, Texas, does have 3 Hinds, none of which is apparently of Libyan origin. 2 of the helicopters were acquired from the German Luftwaffe on the 12th of April, 1991. This became the easiest way to obtain Hinds since German reunification, made Soviet military equipment operated by the former LSKLV readily available to the West. This aircraft, number 616, is believed to have originated in the former East Germany, but the museum staff would not tell me for certain. The aircraft had been donated to the museum from the U.S. Army, provided no questions were asked as to how the U.S. government acquired it. The sheer size of the Hind cannot be stressed when compared to other helicopters. Starting at the front of the aircraft, the large bubble greenhouse cockpit gives the Hind its unique shape. Here's a good view of the gunner's primary windshield. This window is over an inch thick, made of alternating layers of plexi and glass. The window is electrically heated during winter conditions. Supposedly, the armored glass could prevent a 12.7 millimeter round from entering the cockpit. The quarter panels to the left and right are only of plexiglass, supporting the frequent use of the straight-in attack at high speed. The Hind makes itself its smallest target while facing the most of its armor towards the enemy in such an attack. Despite the bubble canopy, even from the exterior, one notices how poor the view of the gunner has of the battlefield. The gunner's views through the lateral plexiglass windows are much better. Here you see how cluttered the gunner's cockpit is from the exterior. The U.S. Army utilized this Hind along with others in locations like Fort Polk and the National Training Center to teach defensive tactics to American troops on the battlefield. This cannon is nothing more than a fiberglass mock-up. Flight testing of the TKB-063 cannon took place between 1975 and 1977 aboard Mi-24B and Mi-24D helicopters. The weapon was installed both in a chin turret and in a cannon pod on the stub wings. In peacetime and under shooting range conditions, the Yak-B proved to be a reliable weapon. Its first hard test, of course, was in the Soviet war in Afghanistan, during which the machine gun revealed several weaknesses that had not come to light during testing. Not until the extreme conditions of Afghanistan was it revealed that some parts of the weapon worked near their sustainable thermal and physical limits. Overheating, which could lead to shooting hot and resulting jams, was the order of the day. Occasionally that there were even cases of ammunition in the chamber self-igniting, leading to uncontrolled firing of the weapon. To prevent these problems, many units reduced the amount of ammunition carried in the Mi-24 from 1,470 rounds to around 400 to 500. Pilots saw this as suboptimal because the Yak-B's high rate of fire, 4,000 rounds a minute, meant that this amount could be used up within 6 to 7.5 seconds. Gunners were therefore directed to limit themselves to short bursts of a maximum of half a second in duration. It was also very problematic that the weapon proved less robust when dirty than other Soviet firearms. For this reason, too, the weapon jammed frequently. Although the Yak-B was capable of engaging targets up to a distance of 4,000 feet in the Hindu Kush, the weapon was used mainly at shorter distances. Up to a range of 2,600 to 3,200 feet, the weapon was very accurate and was devastatingly effective. Veterans of the Afghanistan War report that soft vehicles were literally cut in half by fire from the Yak-B. It is believed that this is the actual ventral bottom of the original gun. Here the massive vent for the spent 12.7mm casings can be seen. The U.S. Army painted this Hind in an all-light gull gray rather than the light robin blue often seen on some of the early Soviet-era Hinds. This is the low-speed wind sensor for the older 9M17M Falanga ATGM missile system, known in the West as the AT-2 Swatter missile. The semi-active command line-of-sight system used this sensor to provide crosswind speeds to the analog missile guidance computer. This is the starboard pitot probe. The Hind has a corresponding probe on the port side, with one providing airspeed to the pilot and one to the gunner. Redundancy of equipment is common on this helicopter, seeing how it was designed to fly and fight in a World War III scenario. Here are the SRO-2 chrome odd rods antenna for IFF. These could potentially be an identification of a true Mi-24 versus an Mi-25 export version known to have been sold to Afghanistan, Cuba, and India. This is the Raduga Complex's optical tracking system with its protective doors shut. Essentially, it's an upside-down periscope for sighting the AT-2 Falanga missiles. This is the swiveling radio command guidance antenna for the AT-2 Falanga missiles on the left side of the gunner's cockpit. The small white dot under the torpedo tube is a sensor for the SBO-10 Sirena 3M radar warning system. The rectangular doors below the two thick black lines are the steps for the gunner to use upon entering the front cockpit. A close view of the port entry steps. The massive canopy of the gunner's cockpit. This window is plexiglass and not bullet resistant. Entering the cockpit is not easy, as the height of the helicopter was quite a climb. There's a lot to discuss in this image. The large wraparound window is the pilot's canopy. Unarmored plexiglass allows for good visibility out the sides of the helicopter for the pilot, but the forward view through the center armored window is atrocious. Here a substantial amount of cluttered equipment is seen. There's nothing clean and sexy about the Mi-24. Everything about it tells the story of functionality above the World War III battlefield, with little room for any other considerations. The large round domes are a part of the particle separation system guarding the intakes of the TV3-117 Victor turbine engines. Note the relatively smooth and flat appearance of the panel directly under the pilot's canopy. Note that there's no riveting until the next panel to the right of the image. This large flat panel is made of 1/4-inch ballistic steel, guarding the sides of the pilot and gunner from enemy fire. This long panel is a load-bearing member. Removal of it will cause the entire nose of the aircraft to droop. A closer look at the engine intakes. Often these are painted as silly cartoon eyes by various nations. Another look at the dimensions of the armored steel panel and the clear texture differences where it joins the rest of the riveted structure. The exhaust of the TV3-117 Victor turbine engine. Early versions of the Hind D did not shield its main exhaust from detection and attack by American Stinger missiles, resulting in substantial losses when introduced into the Afghanistan theater of operations. A small rectangular-shaped piece of industrial Velcro can be seen on the right border of this picture. These are remnants of the Miles laser training system left on from Army training exercises. To the right of the exhaust should be an ample amount of soot and grime. Clearly the aircraft has been thoroughly cleaned before being donated to the museum. The small round hole is the auxiliary power unit exhaust. The port cabin doors are seen in their open position. Locking the doors downward is imperative as they tend to spring backwards, leading to tumbles and bruises to the occupants. The sign "Explosive cartridges installed" does not refer to explosive bolts releasing the doors, but rather that the aircraft is theoretically armed. I was told that there were no cause for alarm and that the sign was for drama purposes only for the exhibit by the staff. Extensive use of hashtag riveting is clearly seen. This is the UB-32 rocket pod. In theory, it would be armed and loaded with S-5 rockets, originally intended to be air-to-air weapons on the MiG-19. Development of this system started in the early 1950s. Although unguided rockets lacked accuracy, in many cases they did in fact bring down enemy aircraft, including an RB-66 reconnaissance aircraft. With the advent of guided air-to-air missiles, the S-5 was forced into the role of an air-to-surface rocket. For the most efficient possible use of the rockets, larger pods holding more rockets were developed, including the UB-32. The aluminum tubes on the outboard missile pylons are visual modifications, or VISMODs, used to train U.S. Army personnel to recognize this version of the Hind as the Victor version. The tubes are meant to be AT-6 spiral missiles that technically could not be fired from the D version of the Hind. A closer look at the UB-32 rocket pod, sadly without any rockets. The S-5 consisted of a steel tube with a solid fuel engine and nozzle at one end. The rocket engine had a burn duration of about 1.1 seconds, which was sufficient to carry the rocket over a maximum combat range of 1.9 miles. At the end of the rocket engine, just in front of the nozzle, were 8 folding fins that extended rearward. They deployed after the rocket was fired and gave the projectile a stable rotation movement around its longitudinal axis. There were many different warheads for the S-5. They ranged from pure fragmentation with impact fuses, hollow charge heads with additional fragmentation casings and piezoelectric fuses, to radar decoys and battlefield illumination warheads. Their penetrative capability against armored targets leaves something to be desired, however. For this reason, the S-5 was replaced by the larger S-8. The Russian Cyrillic warns of dangerous rocket backblast when armed with hot cartridges. A closer look at the VISMOD AT-6. The gun camera port and another radar warning sensor. The starboard front radar warning sensor. The port navigation light. A Soviet-style livery with no distinct indication as to what country this OP-4 aircraft fights for or originated from. The red star simply says, "In case you didn't know, I'm a bad guy. Shoot me before I shoot you." The Mi-24's main rotor was directly derived from the Mi-8's. It has 5 rotor blades that were equipped with flapping and drag hinges, as well as with drag dampers and automatic adjustable blade flapping limiters. As seen from above, the rotor rotates clockwise, which is opposite to the direction of rotation of Western helicopters. The rotor blades can be de-iced electrically. They're designed to withstand small arms fire. Made of aluminum, the blades are made up of individual segments, each with its inside filled with honeycomb structure, 18 sections together with a rotor blade. To better reveal the formations of cracks in the rotor blades, the blade spars are filled with compressed air. A closer view of the rotor head. Port rear maintenance and storage compartments with ample Russian riveting. Why the riveting stops along these 3 rectangular panels is not abundantly clear. The start of the tail boom with a series of antennas that I'll discuss in a few minutes. The strap-on infrared countermeasure pod was a later addition after too many Hinds were lost from Stinger missiles. Note how the dispenser has been physically strapped onto the tail. This is not a modification from the U.S. Army, but how the Soviets engineered the mechanism. Chaff was not carried. The complicated and heavy primary landing gear of the Mi-24. The modern Mi-35 variant has fixed landing gear that does not retract in order to save weight. The actuating tail of the Hind, made of lightweight fabric. Clearly, the paint job has seen better days. The massive tail rotor. Originally placed on the starboard side as a pusher rotor, engineers switched to the port side as a tractor rotor after finding it was much more efficient. A close view of the tail rotor hub. The stinger of the Hind, a common steel V used to prevent a pilot from burying his tail into the ground when approaching for landing at too high of an angle. Another radar warning receiver below the U.S. Army installed infrared slime lights. The rectangular box glows only in the IR spectrum when energized. The rear identification friend or foe odd rods antenna. The rear navigation light. The flashing anti-collision light, Army installed, a replacement of the original Russian light. The spiked antenna is for the VHF radio, and the one on the right is for the UHF radio. The pedestal for the infrared pulse generator. No such system was fitted when the Army took ownership of this helicopter, most likely. A long strip of industrial Velcro is clearly seen above the starboard main landing gear door. The staff accompanying me around the aircraft did not know what it was until I explained it was a part of the Miles laser training system installed by the U.S. Army. Sensors for laser emissions were attached to the Velcro strips like these. A close-up view of the Velcro strip for Miles sensors. The static discharge probe on the starboard stub wing. This photo shows how the cabin windows open upward and inward to make use of Kalashnikov rifle mounts. This is a close-up of the expanding pneumatic seal inside of the cabin doors. Air is pumped into these rubber lengths, expanding them to seal the helicopter from nuclear and biological contamination. The Hind is pressurized, but lacks an internal oxygen system for high-altitude flight. Entering the pilot's cockpit on the right side was not easy. Note the same pneumatic rubber seals seen in the cabin doors are seen here. To the top of the photo is a series of rectangular electrical fuses. These are accessible to the flight engineer who usually occupied the tunnel, which is not seen and to the right of the picture's border. The switches are for individual electrical systems. All switches in the entire panel could be switched to the up position with a simple handle mechanism on the pilot's right rear. Such switches are only usually manipulated upon startup. Another look at the fuses with the pilot's seat to the right in the image. All original Russian hardware. The steel bar under the fuses is the stabilizer for the armored cockpit door. A difficult shot to make of the instrument panel. The teal-green cockpit color is said to be purported to be for pilot relaxation during stressful situations from Soviet psychologists, but most Russians agree that the color is so that in the red night lighting, the panels appear an easy-to-see gray. The right side is dominated by what U.S. Army pilots call the Doppler Etch-a-Sketch. The inertial Doppler system in the tail of the helicopter follows the velocity of the aircraft, plotting the movement on the display with a properly scaled map card. The red box around the black cross physically moves on the map, showing the pilot the aircraft's current location, in theory. The longer the flight, the less accurate the location becomes. Manual tuning over known landmarks is essential. While some operators claim they did not use the system because it was flawed, other pilots vouched that the system was extremely accurate. The white piece of paper covering the center panel is a translated diagram of the warning lights to its right. The large black cyclic stick snakes very high between the legs, much higher than expected. Black sun visors wrap the instrument panel above. A clear view of the cyclic stick. The large handle in front of the stick controls release of the Hind's pneumatic braking system. A modern cushion has been added on top of the traditional black leather seat to give the pilot a boost. The pilot cockpit is large and roomy, unlike the gunner station. As a small man, I sank into the comfortable seat, but could not see anything through the front armored glass. Even a tall pilot sits low in the Hind. A booster chair, but it's not just for me. The last pilot must have been pretty short as well. The leather seat was in excellent condition. To the right border of the picture, you can see the U.S. Army added floodlight, and above the seat, thin white cable can be seen. That's also a U.S. Army addition. The panel beyond the seat, from left to right, controls electrical systems and radios. The 8 small round shapes with different colors labeled 1 through 4 are the helicopter's signal flare system. The Soviets developed the system to signal the ground personnel the condition of the aircraft and crew on approach to base. To the left of the cyclic in the picture are a series of switches controlling windshield wipers, the cockpit fan, external formation lights, and fuel. All panels are marked in English. The pilot's right panel is seen from outside the armored cockpit door. Moving from right to left is the U.S. Army installed UHF and VHF radio controls. To its left are controls for the DC and AC power systems. The large dials are electric isolators to check voltage in individual systems. To the far left of the photo are the controls for heating, air conditioning, and cockpit lighting. A close-up view of the power panel. Close-up of the American radio set knobs below numerical indicators. The radio is labeled a blunt 1. It's most likely a UHF. The radio is set to frequency 329.25 with channel 12. This is not Russian hardware. The pilot's weapon control panel. Airflow valves for the air conditioning are not Russian hardware. A significance of the numbers 670, 910, 955, 990 is unclear. To the lower left of the picture, the autopilot stabilization panel is seen. A better view of the pilot's left panel controlling electrics, fuel, signal flares, radios, and fire suppression systems. A small black rectangle box marked video and GPS is clearly added by the U.S. Army. Under the cyclic control, the black collective control lever can be seen on the pilot's left. The curving neck of the high-riding cyclic stick is evident in this photo. Once again, I'd like to stress the large, roomy nature of the pilot's cockpit in the Hind. Very comfortable, surrounded by a high bubble canopy. The large and complex center console further blocking the forward view of the pilot is missing from this aircraft, replaced with a U.S. Army piece of equipment of unknown use, possibly another FM radio. The Hind D had only the PKV reflector gun sight for the pilot and not the more complex HUD found in the Hind V. This is a good picture of the KPS-35AV controls of the Yak-B 12.7mm gun system in the gunner's cockpit. While many may claim Army modification of the unit, it's not true. The unit is tilted upward to an 80-degree angle. The KPS-53AV machine gun control and targeting device located in the gunner's direct field of view. It was operated with both hands and was capable of moving the aircraft's machine gun in the vertical and horizontal planes. A target indication was projected onto the ASP-17 Victor reflector sight, which always pointed in the same direction as the barrel. The solution was not perfectly ideal, since the gunner sitting strapped into his seat and wearing a helmet had insufficient space to be able to exploit the weapon's entire range of movement. When firing to the side, his only option was to fire from the hip, combined with the attempt to direct his fire onto the target by using tracer. The stowable, redundant cyclic controls for the gunner. This is the Cadillac yoke off to the right of the gunner for aiming the inverted periscope sight of the Falanga missiles. The Hind D was without its intended AT-6 missile system when it first was built. The AT-6 missile system would take much longer than intended to perfect, so the Hind D had to make do with the older Falanga AT-2 missile complex seen here. The yoke required the gunner to steer the slow-moving missile onto the target and lacked the accuracy of the future-built AT-6. Missiles were guided by radio command guidance. If the gunner sits facing 12 o'clock, the missile yoke is at 2 o'clock, with the missile sight at around 1:30. The sighting system for the Falanga missile system: a forehead pad that is adjustable for use with left or the right eye is noted. No rubber eye shade is available. The wiring is original Russian hardware. One must lean uncomfortably over the yoke using the large steel armrest to securely brace into the position. As a small man, even I found the front cockpit a very tight fit. To the right of the KPS-35AV gun sight was a U.S. installed altimeter. The black panel with a teal-colored background appears to be a missile readiness panel of some sort. The labels in English read Ready, Launch, and Computing. The cylinder is an Army-installed cockpit lighting system. A wide shot showing both the KPS-35AV together with the panel to the right, seen in the last photograph. A photo showing further Army modification. On the left, a large black panel for radio control. The black panel surrounded by a teal is original Russian hardware, but in English labels. The labels read Test Computers, Firing, Bombing, Coupler On and Off, Altitude, Static Moving Ground. The gunner's left panel: missile selection and the all-important sight door controls. Windshield wiper speed, altitude, speed in knots is clearly an Army modification. The HSI is seen in the 10 o'clock position, which is fairly odd for an aircraft as most pilots prefer it to be in the center line at 12 o'clock. The red guard is for the pedal damper switch. It's set in the off position, the position I prefer when flying the DCS World simulation of the Hind. I saw it in this position and chuckled that the last pilot to fly from the front hated the dampers just as much as I did. Another view of the same panel, but this time with the salvo dial for the rocket pods and controls for using the pylons for bombs. The large and heavily worn red bar here is the master arming switch for the weapon system. The panel underneath controls deviation for the gun in English. The gray wiring to the left is an Army modification. Another view of the panel to the right of the KPS-35AV. The Falanga power unit behind the gunner's right shoulder. All Cyrillic writing has English labels on top of it. Indication lights for missile battery, gyro, radio beam guide, igniter, infrared lamp, complete with test functions. The large electrical cable connections are almost out of a sci-fi movie. The black selector is to choose which missile is to be prepped on the outermost pylons. Below the primary panel is the box controlling power and modes for the inverted periscopic sight. Modes for search versus observe is seen marked with a number 7. An excellent view of the armored glass with the fake Gatling cannon outside. The leather strap is for gripping when entering the cockpit. The venerable Soviet-era rubber fan is seen to the right. Thick cushions were on top of the black leather seats as they had lost much of their support over the years. This photograph is to the right of the gunner's seat. While the wiring is Army installed, where it leads to is not certain. The black handle attaches to a breaker box for activating all systems quickly. The mount of the KPS-35AV controlling the 12.7 millimeter turret below. The gunner's collective lever. The gunner's collective lever. The cabin windows are securely sealed for nuclear, chemical, and biological attack, but have been clearly seeing serious wear over the years. You won't be able to stand inside the back cabin, but rather have to hunch down. The yellow pipe leads to the fuel tanks under the floor panels. The black intercom cable is for kneeling gunners to communicate with the flight crew forward and are not Russian equipment. The tunnel for the engineer to access the cockpit can be seen. I assume that these are additional cabin lights installed by the U.S. Army. The cable bundles are modifications. The ceiling was covered in thin padding. Another yellow pipe connecting the fuel tanks. Additional boxes and piping do not appear to be original to the Mi-24. Thank you for viewing my review of the Mi-24D. To have access to such a rare helicopter was a privilege. I want to once again thank the Southern Museum of Flight for their support in this project. Please consider a visit and a donation to their wonderful organization.